It is section 16.6, parametric surfaces and their areas. Earlier, you studied the curves parameterized as a function of t in an interval. Surfaces can be parameterized as a function of two variables, u and v. In this section, we'll try to describe parametric surfaces in a similar fashion as for curves. Let's see the definition. A parametric surface is a set of points x, y, z in a three-dimensional space such that the components are expressed by a vector function of the form. So each component is a function of u and v, and u and v are in a domain in the two-dimensional space. Here we have examples. This first figure is torus. That is made from that command in Maple. And p, the parameter, is from 0 to 2 pi, and t is also from 0 to 2 pi. Now, that is, okay, let's see which one is which one. Okay, now, okay, here, this is x direction, okay, that is z direction. So that p is that rotation, and then t is this rotation. So along with this formula, that is x component, y component, z component, we can get this surface. Now for this one, we have two variables, t and z. Z is that direction, t is rotational direction. And now r is made in this way so that we can get this y curve. And so that the parameterization is in tz two-dimensional region. And in fact, this is a rectangle, and also this one is a rectangle. Okay. Identify and sketch the parameterization when UV are chosen in this region. Okay. For this one, you can easily identify. Okay, that is x component, that is y component, this is the z component. If we consider x and z, then, for example, x squared plus z squared will be 4 cosine squared u plus 4 sine squared u, which is same as 4. So that in xz direction is a circle of radius 2. So that shape. And now y is moving from 0 to 5. So in y direction, 0 to 5, and x, z direction, it is a circle of radius 2. So you can easily identify the surface. Now the surface is defined over this region. In u direction, it's moving from 0 to 2 pi. In v direction is from 0 to 5, right? So you can easily identify. Let's do one more here. Now for this one, that is x and y and z. So that, of course, here st are two variables and chosen from a rectangle. In first direction from 0 to 2, in second direction from 0 to 2 pi. Okay, now from this representation, okay, x squared, consider this one and that one. So x squared plus y squared. Then that is s squared cosine squared 30 plus that squared is s squared sine squared 30. That must be s squared. Now, that is the same as z. So this one is making a paraboloid. Okay, let's try to visualize the paraboloid in 3D coordinates. That is x direction, y direction, and z direction. Okay. Now, for that one, here t is moving from 0 to 2 pi, so the whole circulation. So we can get that one. So it's a paraboloid like that. Okay. Now, here s is from 0 to 2, which means that z is between 0 and 4, right? S is from 0 to 2. Okay, here, that's from 0 to 2. So s squared is z, so it's from 0 to 4. That means this is 4. So that only the surface is making this part of this paraboloid. Now here a question is, what is the effect of the number 3 involved in this one? Okay, t is from 0 to 2 pi. Without 3 here and here, this whole, this and x and y will make a whole circulation. But because of the 3, now 3t is moving from 0 to 6 pi, so that the 3, number 3, is making 3 times duplication of this surface. So that the net effect of the number 3 is just 30 times of rotation. So once you try to get one-to-one mapping, then you may restrict the t from 0 to 2 pi over 3, or you may eliminate this 3 here, right? Then you can make only one copy of this paraboloid, okay? Okay, let's move on. Now, so far, we try to identify the surface when the representation is given. Now, in opposite, for given surface, we try to find the parametric representation of the surface. Okay? Find a parametric representation of the plane which passes P0, contains a vector and another vector. That's quite easy. Basically, here we can use this formula. The plane can be made and with 2 vectors. We can use these 2 vectors in this formula, or we may try to get the normal vector by computing the cross product. You can do it either way, but at this time we'll try to do this one simply using this formula, so that R UV is the same as P0 is 1, 1, 0. Oh, okay, not 0, is 1. The final component is also 1. And then now plus U, and the vector is 1, 2, 0, and V, and that is 2, 0, minus 3. we can simplify that one. The first one is 1, okay, not u, 1 plus u plus 2v. Second one is 1 plus 2u, and there's no contribution from v. And last one is 1 plus no contribution from here, and now there's a minus 3v, right? Okay, so we have that, right? So that is a representation of the plane, okay? Find a parametric representation of this, okay, that is a sphere of radius a. So in this case now we choose rho as a, and we may try to use the spherical coordinates, and we can find a map as a function of theta and phi. Okay, let's try to do that. When we get the spherical coordinates, and here once rho, the length is known, then here z is rho cosine phi. Phi is the angle from North Pole to the line segment from 0 to the point. Okay, now r, we try to use the intermediate variable, that is rho and sine phi. You remember this one. Now rho is a, so it's a cosine phi, and r is now a sine phi, right? What is x? X is r cosine theta always, so that r is this one, a sine phi and cosine theta, and y is always r sine theta, which is now r is a sine phi and sine theta. And so we have three components, and x is here, y is here, z is here, so that there is first component, second component, and third component. Of course, theta must be from 0 to 2 pi, whole circulation, horizontal circulation, and phi is angle from North Pole, so it's from 0 to pi. So that's a parameterization using the spherical coordinates, right? Okay. Okay. Find a parametric representation of the cylinder. Okay. Now z is moving from 0 to 1. So looks like now radius is 2. And here theta is from 0 to 2 pi. So we may try to use the cylindrical coordinates. Okay. Then now radius 2. So that x is now 2 cosine theta, and y is 2 sine theta. So radius 2. So x squared. From this one, now x squared plus y squared must be 4. So these two will satisfy the first equation. Now in z direction, we have just z, so that the parameterization r is a function of theta and z. That will be x component is 2 cosine theta, y component is 2 sine theta, and z direction we have z. Okay, that is parameterization, and the domain must be in theta direction. We have from 0 to 2 pi, whole circulation, and in z direction, we have that one from 0 to 1, so that we have to put here 0 to 1. Okay, that's parameterization using the cylindrical coordinates. Okay. Find a vector representation of the elliptic paraboloid z equal x squared plus 2y squared. And for that one, we may try to get, because it's explicitly given, so that we may consider the parameterization as a function of xy. Then we can put here x and y, and then in z direction, okay, that one, x squared plus 2y squared. Then it is making a surface exactly the same way as in this equation. Okay. In general, we can naturally parameterize for surface given explicitly in this way. Z is f of xy. Then a natural parametric representation of the surface is this one. Now xy and f of xy. Parametric representations are not unique. You can find more than one. And let's see this example. Find a parametric representation of z is 2 square root of x squared plus y squared. Okay, this is the corresponding surface. So for that one, we may try to use polar coordinates for xy. So that number one, now we may get, for example, now x is here r cosine theta, and y is r sine theta. Okay, then now x squared plus y squared is r squared, right? And from here, now z equal 2 square root of x squared plus y squared becomes 2r, right? So the final parameterization is now, along with as a function of r and theta, we have first component is r cosine theta, and second component is r sine theta, and the z is 2r. Then that is a parameterization. Of course, the theta must be from 0 to 2 pi, whole circulation. That is one way of getting a parameterization. Secondly, now as in here, we try to get a natural parameterization. There's now all of xy. Then first component is x, second component is y, and then there is z, 2 of square root of x squared plus y squared. Right? That is another parameterization. So the representations are not unique. You can introduce many of representations. Okay. Okay. Now we consider surfaces made from revolution. Look at this figure. Now there's x direction, there's y direction. Y equal fx is given, the graph of x equal y, y equal fx. That is rotated along the x-axis. Then we can have such a surface. So rotation of a curve can be used to get a surface. So such surfaces are called surfaces of revolution. Let's see a mathematical formula for that. S is the surface obtained by rotating y equal fx from a to b, x is from a to b, then in about the x-axis, then s can be represented as in this form as a function of x and theta. Okay, x is not changing, but now fx is used as radius. The height in y direction is playing the role of radius, and now from the positive y-axis start rotating. So that we have put here cosine theta. In z component we have sine theta. Of course, x is originally the same range, and theta must be from 0 to 2 pi to represent whole circulation. Right? Okay. Find parametric equations, for the surface generated by rotating the curve y equal sine x. X is from 0 to 2 pi about the x-axis. Okay, using this formula, we can get it quite easily. R, x, and theta. That is, x is not changing, just x, first one. And y component is, this is f of x, so that's sine x times cosine theta. And again, fx, sine x, times sine theta. And here, in originally x is between 0 and 2 pi, so that x and theta is in 0 to 2 pi. That's from original definition. And then for whole circulation, theta must be 0 to 2 pi, right? Okay, that's parameterization using this formula. Okay, we'll continue in the second part. Thank you.